1 minute ago, monitoring teams at Mount Etna detected something that froze every volcanologist in Italy. A fresh fracture nearly 30 meters long has ripped open across the volcano's southeastern flank, slicing through ancient rock with unsettling precision. The line runs parallel to the scar of a collapse 8,000 years ago, a collapse that unleashed a tsunami tall enough to swallow a 10-story building. What if this is not just another crack? What if the entire flank is beginning to slide into the Mediterranean? And if 500,000 people are living on ground that could disappear in minutes, why can no one stop it? The first drone footage arrived at 0430 UTC. Thermal imaging along the Valle del Bove revealed the rupture stretching from 2,400 meters in elevation down to 900 meters, cutting through compacted ash and basalt that had remained intact for millennia. The fracture measures nearly 30 meters in length, up to 2 meters wide in places with fresh downslope displacement of at least 15 centimeters. What alarmed scientists at Italy's National Institute of Geophysics and Volcanology was not only the size of the crack, but its exact position. It follows the boundary of the ancient collapse zone almost perfectly. An INGV geologist stationed at the Piazzi Denari Observatory described it as a nightmare scenario. The fracture sits directly atop a known slip plane, a buried layer of weakness beneath Etna's eastern face. For years, researchers had tracked slow seaward movement of the flank just 3 to 5 centimeters per year, dismissing it as gradual spreading. But this rupture appeared overnight. No warning tremors, no magma intrusion, no surge of volcanic gas, just a clean break in the skin of the mountain. Within 3 hours of the discovery, Italian civil protection authorities moved in. The upper slopes of Mount Etna were closed. Red exclusion zones encircled the fracture, cutting off hiking trails, mountain refuges, and the cable car station at 2,500 meters. Airspace restrictions expanded 5 kilometers around the summit, grounding tourist flights and forcing scientific helicopters to operate under special clearance. LiDAR-equipped drones were deployed in rotating shifts, scanning the fracture every 2 hours for any sign of widening or propagation. Ground-based laser rangefinders were positioned on both sides of the rupture, locking onto fixed reference points to detect even the smallest motion. Field teams were lowered into the fracture within hours, installing crack meters across the gap at 3 different depths. Each instrument measures displacement to the nearest millimeter, transmitting data every 10 minutes via satellite link. Additional GPS stations were bolted into stable bedrock, flanking the rupture, forming a monitoring network capable of detecting lateral motion as small as 5 millimeters. At INGV headquarters in Catania, live feeds from 8 cameras now fill entire walls of screens, all trained on the fracture zone. Infrared sensors scan continuously, searching for heat signatures that might signal rising magma or escaping gas. But the instruments are detecting something else entirely. Satellite INSAR data from the European Space Agency shows ground deformation radiating outward from the fracture. Between November 15th and November 26th, the downslope side of the crack moved 4 centimeters seaward, while the upslope side remained effectively stationary. The pattern is unmistakable. This is not volcanic inflation forcing the mountain apart from within. This is gravity pulling a massive slab of rock toward the sea. Coastal GPS stations 12 kilometers from the fracture recorded synchronized eastward shifts of 2 centimeters over the same period. The movement is coherent across the entire southeastern flank. Crack meter data confirms a stepwise opening: 8 millimeters on November 19th, another 6 millimeters on November 23rd, 4 millimeters more on November 25th. Each increase occurred in silence, without earthquakes, without tremor, without any of the usual volcanic precursors. Photogrammetry teams built high-resolution 3D models of the rupture using drone imagery, then overlaid them with topographic data from 2019. The comparison revealed a chilling alignment. The fracture lies directly atop the same buried fault plane that failed 8,000 years ago when Etna's eastern flank collapsed into the Ionian Sea. Every dataset points to the same conclusion. The ancient slip plane is reactivating. Field samples taken from the walls of the fracture revealed what the instruments alone could not. Core drilling along the rupture exposed a layer unlike the solid basalt surrounding it. This gouge layer, trapped between intact volcanic rock above and fractured sediment below, is rich in clay and has a texture closer to wet sand than stone. Laboratory tests at INGV showed its shear strength is less than 1/10 that of intact basalt. Under stress, it behaves like a lubricant, allowing the enormous mass above to slide with minimal resistance. The southeastern flank of Etna is not anchored to bedrock. It is resting on something that can move. Gas measurements inside the fracture added another warning. Elevated concentrations of carbon dioxide and hydrogen sulfide were detected rising from depth along the rupture plane. Carbon dioxide levels reached 18,000 parts per million near the fracture floor, 3 times higher than background values on the surrounding slopes. These gases are not coming from shallow magma chambers beneath the summit. They are migrating upward through fractures in the slip plane, driven by tectonic stresses compressing the base of the flank. Etna's internal structure is being disturbed from below. Thermal imaging revealed localized hotspots where temperatures reached 62 degrees Celsius, far above the ambient surface temperature of 18 degrees. These anomalies cluster at the base of the rupture, exactly where the slip plane intersects the new fracture. The heat is not rising from magma, it is being generated by friction, rock grinding against rock as the flank slowly moves. The mountain is already in motion. What followed forced scientists to confront a hard truth about how volcanic flanks fail. A volcano like Etna is not a single solid mass. It is a pile of lava flows, ash layers, and pyroclastic debris stacked over hundreds of thousands of years. When that pile rests on a weak inclined foundation, gravity becomes the dominant force. The southeastern flank of Etna is estimated to contain 25 cubic kilometers of rock, roughly 70 billion tons. This enormous mass sits on a base that dips 15 degrees toward the sea, steepening to 25 degrees beneath the sea floor. It is an inclined slab balanced on a tilted ramp. With every eruption, new material is added to the summit. The pressure on the slip plane increases. Recent research shows that magma is not required to make the flank move. Gravity alone is enough. Between 2016 and 2017, geodetic instruments deployed offshore recorded something that overturned decades of assumptions. During an 8-day period in May 2017, the offshore extension of Etna's fault slipped by 4 centimeters. There were no earthquakes, no summit eruptions, no magma rising through the volcanic conduits. The flank moved because gravity pulled it. For years, scientists believed magma pressure was the main driver of instability, that Etna's flank only shifted when volcanic forces pushed from within. But the seafloor data, combined with onshore GPS measurements, revealed the opposite pattern. Movement is strongest near the coast and weakens toward the summit. If magma were responsible, the largest displacement would appear near the volcanic center. Instead, the system behaves like a slow gravitational collapse, its underwater base sliding seaward and dragging the entire flank with it. Computer simulations of a catastrophic failure paint a grim future for the Mediterranean. If 25 cubic kilometers of rock were to slide into the Ionian Sea at speeds approaching 200 kilometers per hour, the resulting displacement would generate tsunami waves between 20 and 25 meters high. Modeling by INGV shows these waves reaching the coast of Calabria within 30 minutes. Greece would be struck in about 90 minutes. North African shores would be impacted within 2 to 3 hours. The entire eastern Mediterranean would lie within the danger zone. These figures are not speculative. They are constrained by geological evidence from the collapse that occurred 8,000 years ago. Submarine surveys have mapped massive debris fields extending 20 kilometers offshore from Sicily. Huge blocks of Etna basalt lie tangled with marine sediments, all dated to the same period. Sediment cores from the Ionian Sea contain chaotic layers that only form when a tsunami violently stirs the sea floor. The Mediterranean has experienced this disaster before. Across southern Italy, gravel layers containing Etna ash rest above Bronze Age settlements, evidence of waves powerful enough to carry cobbles kilometers inland. On Malta, coastal lagoon cores show abrupt shifts in salinity and sediment around the same time. In Greece, shoreline deposits of identical age contain reworked volcanic material chemically linked to Etna. The ancient collapse left fingerprints across an entire sea. One site tells the story more clearly than any model or simulation. Atliat Yam, a Neolithic village now submerged off the coast of modern Israel, was abandoned suddenly around 8,000 years ago. When archaeologists excavated the ruins in the 1980s, they found signs of abrupt flight. Fish had been gutted and sorted but left behind. Stone tools lay scattered in workshops. Grain storage pits were only half empty. Radiocarbon dates from the site align precisely with the age of Etna's offshore debris field. Researchers now believe the village was destroyed by the tsunami triggered when Etna's eastern flank collapsed. Waves traveled more than 1,800 kilometers across the Mediterranean before striking the Levantine coast. The ancient disaster was not a legend, it was a documented chain of cause and effect. And today the ground is revealing another weakness. Italian civil protection agencies do have evacuation plans for Mount Etna, but those plans were designed for lava flows and ashfall, not for the sudden failure of an entire mountainside. Relocating 500,000 people from the red zone, the densely populated area sitting directly atop the unstable flank, would overwhelm regional infrastructure. Catania, Sicily's second-largest city with 310,000 residents, lies less than 30 kilometers from the coast that would be struck first by tsunami waves. The city has only two main evacuation routes inland, both narrow highways that funnel through mountain passes. During a 2019 emergency drill, a simulated evacuation of Catania required 14 hours under ideal conditions. A real collapse would offer no such conditions. Initial flank failure would likely trigger earthquake swarms, damaging roads and bridges. Panic would clog highways with abandoned vehicles. Coastal residents fleeing inland would collide with mountain communities trying to reach higher ground. Emergency responders involved in preparedness exercises have admitted privately that in a real collapse, they would be focused on their own survival. Coordination would fail within minutes. Maritime evacuation offers no solution. Catania's port could move perhaps 20,000 people over several days if advance warning existed. In an actual collapse, tsunami waves would arrive within 30 minutes, long before ships could be loaded or reach safe waters. Along the Ionian coast, fishing villages have no tsunami sirens, no elevated evacuation zones, and no designated maritime rescue points. The system is not built for what may be coming. Long-term monitoring data shows just how unstable the situation has become. Continuous GPS measurements reveal that Etna's southeastern flank has moved 1.2 meters seaward since monitoring began in 1981. That averages to about 2.8 centimeters per year. But the motion is not constant. It accelerates during eruptive phases and continues even when the summit craters fall silent. Seafloor instruments have recorded slip events lasting days or weeks, during which the flank shifts several centimeters without producing any felt earthquakes. The mountain is sliding quietly. At Refugio Sapienza, a mountain refuge at 1,900 meters elevation, this movement is no longer an abstract concept. Manager Giuseppe Torresi has watched Etna for more than 3 decades. His family has operated the lodge since 1956, serving hikers, skiers, and tourists drawn by the volcano's spectacle. The new fracture changed everything. On the night of November 18th, he heard a deep sound like thunder. Not an explosion, not a rockfall, a low rumble that seemed to come from inside the mountain. By morning, guides had found the crack. Soon after, officials told them to prepare for the possibility of permanent evacuation. Mount Etna holds one of the longest continuous records of volcanic activity on Earth, with written accounts dating back to 1500 BCE. Ancient Greek historians described eruptions that darkened the skies. Roman scholars recorded ashfall reaching North Africa. Over the past 500,000 years, Etna has repeatedly built and rebuilt itself. Each eruption layered lava and ash onto its flanks. The current stratovolcano structure began forming about 15,000 years ago. Since 1600, Etna has produced at least 60 flank eruptions and hundreds of summit eruptions. Nearly half occurred during the 20th century alone. From 2000 to 2024, the volcano erupted almost continuously. Each eruption reshapes the mountain. Each eruption adds weight. The volcano is constructing its own instability. The most recent eruptions introduced a new and troubling variable. Lava samples collected during the August 2024 events show mineral compositions that do not match Etna's typical basaltic signature. Petrographic analysis reveals pyroxene and olivine crystals with unusual zoning patterns, evidence of rapid changes in magma chemistry at depth. Whole rock geochemistry indicates silica levels roughly 3% higher than Etna's historical basalt, trending toward andesitic composition. Laboratories in Rome were unable to classify the material within existing Etna categories. The behavior of the lava was equally unexpected. Instead of forming the long pahoeho or AA flows characteristic of basaltic eruptions, the August flows were short, thick, and blocky, textures more commonly associated with higher viscosity magmas. Even more concerning, pyroclastic flows rare at Etna occurred twice during the summer sequence, sending superheated avalanches down the southeastern flank. Seismic data from this period shows tremor sources at depths of 15 to 25 kilometers far below Etna's main magma storage zone at 3 to 6 kilometers. This suggests deeper magma systems may be becoming active, or that Etna is tapping a more evolved source. If magma chemistry is changing, the consequences for flank stability are serious. More viscous magma can trap gas, increasing explosive potential. Clogged conduits can allow pressure to build rapidly, and any shift in the internal stress regime could alter forces acting on the slip plane below. Scientists monitoring the data cannot say what comes next. They can only say that the system is behaving differently than it has before. This fracture may not be an isolated event. It may be the first visible symptom of a deeper transformation. As of November 27, 2025, the data shows no sign of stabilization. The southeastern flank of Mount Etna is now moving seaward at more than 7 centimeters per year, the fastest rate ever recorded by continuous monitoring. The fracture first discovered on November 18th has widened by a cumulative 31 millimeters. INSAR analysis confirms that coherent deformation now spans nearly 180 square kilometers, extending far beyond the visible crack into a vast subsurface fault system that reaches beneath the seafloor. Evacuation strategies designed for lava flows and ash clouds are not equipped for this scale of failure. A flank collapse would unfold far faster than any volcanic crisis Sicily has prepared for. Tsunami warning systems in the Mediterranean remain fragmented, with no unified protocol capable of issuing rapid alerts across national borders. From Sicily to Greece to North Africa, coastal infrastructure was built without serious consideration of tsunami risk. Millions live and work in zones that would have minutes, not hours, to respond. Scientists know the facts. They know the flank is moving. They know it rests on a weak, lubricated foundation. They know gravity is pulling tens of billions of tons of rock toward the sea. They know that 8,000 years ago, a collapse from this same volcano devastated the Mediterranean basin. What they do not know is when the transition from slow creep to catastrophic failure might occur. It could happen within hours, or it might never happen at all. Modern monitoring can measure change, but it cannot identify the tipping point. Computer models can simulate disaster, but they cannot predict the trigger. If the flank were to fail tonight while Catania sleeps, ferries are docked, and emergency responders are off duty, would 500,000 people have time to escape before the waves arrive? That is the question scientists cannot answer.